Hello and welcome back. So, it has been a while since our last delivery, related to this small project, the not so simple flight mechanics of Ironman. So, in the previous video, we defined design guidelines, everything. I gave a brief overview. So, basically, just revisiting here what we're doing and some guidelines and in assumptions and hypotheses. So the most important one, and I think is very conservative, is the weight of the whole stuff. Weight and height, but most importantly, weight. This is the one that is going to drive the design, how to generate the lift, the drag, and everything. So we assume 120 kilos after some design using space cleans, assuming thickness of the armor, material, and so on. Personally speaking, I think it's very conservative, should be at least twice, but let's bear with this. And also working with cruise speeds between 0 and 500 kilometers per hour. And also we define a few domains. So I'm sharing some data on the internet, and we have a repository, and two domains I defined, so the circular and this rectangular one. But for all the aerodynamic study, I will be using this domain, and just use this one because this is one we need to change the angle of attack. So this one I rotate the whole stuff, and it's very simple. Instead in here, if I want to change things, it's a little bit tricky. I will need to remesh or probably divide the the boundaries. So this one I would use it just for overset meshes for the dynamic part. So there will be another mesh around Ironman here. So that being said, all the results that I'm going to show are related with this domain. Okay, so we have a mesh. It's a very good mesh. Okay, polyhedral mesh. The mesh is also wall resolving. We use a very good meshing tool. And from the previous video, I mentioned that to construct some polos, but I was a little bit conservative in the sense, or I didn't have an idea, so I was mentioned, let's go like 20 degrees, probably 10. But turns out that I have to go from some negative value, actually starting at 0 to 90 degrees. Okay, and here we have all the output of this study. So we have a Mach 0.3, and here we have lift. So remember that our target is 120 kilos, something about, let's say, 1500 newtons. So see that basically for this speed and these conditions, we're at sea level. So as you get higher and higher, things get even worse. Okay, density change, and it will get worse. So in theory here, we need to be about 30 degrees to generate the necessary lift. Okay, but this comes with a penalty, that is drag, and drag is very, very big in this case. So Ironman is not aerodynamic at all. So at this, and that can we measure that efficiency by looking at lift to drag ratio. So for those that do aerodynamics, that an aspect rate, a good lift to that drag ratio of an airplane, general aviation, or commercial airliner, it will be something about 8. Okay, and see that here we have less than 1. So basically you are generating more drag than lift. So it's not aerodynamic at all. Okay, it can be improved a lot, but we have a constraints of the anatomy, the head, whatever. We cannot move it, so we cannot do anything there. We need to look at another way to solve our problem of lift generation, because drag, you have it there. Okay, so then also we want to another Mach number, 0.6. We double the velocity. So as you recall the equation of lift. Okay, later we're going to see that one. So you double the velocity, you should quadruple your forces. Roughly speaking, not necessarily, okay, because if you have non-linearities, you start to have mass separation, shock wave, or whatever other nonlinear phenomena will have an influence. But basically this, we are going to see some similar behavior, but when increasing velocity, things get better. Now we see that at 0 degrees we generate that necessary lift. Okay, in this case we were far away. Okay, but also we generate a lot drag. So comparing now Mach 3, Mach 0.6, the velocity, and here I compute this factor now between these two velocities, just to show that basically you double velocity, quadruple the forces. You have it here, okay, roughly speaking, and you start to see that at 30 degrees it starts to go down, because we start to see non-linearities. I know that at Mach 0.6 I already have some local regions where the Mach number is more than one, and that creates problems, okay? But this is also not from aerodynamics. We know that that behavior, we have it there, okay? So we know that Mach 0.3 or actually less than 0.6, you are not going to generate that necessary force, okay? Mach 0.6, we have it. So assuming that we are going to do a lot of design at this velocity, actually we don't know about velocity Ironman is flying, okay? So assuming that I will go here, this is where it's going to represent problems. If I stay in this one, okay, it's going to fly. It's no problem. Remember that this is sea level, and look at the equation of force. So if you change any of these variables, you're going to have an influence. Okay, so here clearly you can see you double velocity, you're going to quadruple your variables. But if you're changing in altitude, density will change, and then you're going to penalize all your forces. The surface area, let's say that this will remain constant, and this is the coefficient of force, or whatever you're computing, lift, drag, or whatever. So here's where you're going to have all your non-linearities. And I know that when it comes to lift and drag and compressibility effects, there is a very strong non-linearity here. So if I keep increasing my Mach number, and I already have some results, Mach 0.75, this coefficient will go down a lot, and all the forces will go down. So it's a really bad condition, okay? But let's just sit here, but for those curious, now you can go 0.775. If you want, you can go supersonic, but let's solve first the problem, how to balance everything, because that is our goal, okay? We want to balance, we want to keep about 0 degrees and balance, generate somehow the forces. So this is already telling us we need to use vector thrust like in the first video. So just putting everything in a graphic here, we have the famous polars. So angle of attack, and then drag, lift, now to my left, lift, drag forces, and we plot it here, and we have our behavior, okay? It's nothing to say, I hope you're familiar with aerodynamics. So as you keep increasing the angle of attack, lift is still increasing, in this case Mach 0.3. It's a really bad condition actually. Look at that, you need to go to 40 degrees to generate that necessary force, okay? So this is basically not what we see in the movies. And just to reiterate that Hollywood is lying, obviously not it's lying, but they should probably they can put a little bit more realism in what you're doing. And here we have the drag, and the drag increase like crazy. So as expected, 0 degrees will be the lowest one, okay? But then it is increasing like crazy, so you have here the scale. We compare the lift to drag ratio, the quantity that we're using now to measure the aerodynamic efficiency. So this is a flying rock Ironman, it's not aerodynamic at all, and we cannot do anything. So we know that if we put some wings, it's going to perform much better, but we cannot put it. So look at that, this red line, we have at a Mach 0.6. And here clearly you start to see those effects that I was mentioning, non-linearities. When you start to increase, already have seen that Mach 0.6, I have I reached my critical Mach number. I have local regions where I have shock wave, and that will have an influence in my forces, and see that it reduces. And it seems get worse when you keep increasing the Mach number. So this is the summary, the results that we have. Okay, then well, some pretty colors now, this colorful fluid dynamics. So here we have now the pressure contours. I'm mentioning that now the next step will be to balance this, okay? So I will run another campaign of simulations. Also, if somebody wants to help me, let me know. I'm sharing all the data. So my next step is going to be overset meshes. So I will have that condition, and in overset meshes, I just will paint in the surfaces of Ironman, know some patches there where I'm going to inject some moment just to keep it aloft, okay? Just to know how much energy I need to just to balance, to keep it now generating the necessary force. I already know that now we have the forces, but just to do that study, I'm not going to do rigid body motion just to make it rotate around the center of mass. That will be the next step. I just want to, let's say, calibrate, play around with my overset technique, okay, just to get everything right. But that will be the final goal, that having the fully rigid body motion can go all up and down and rotate around the center of mass. And then those points where you are going to have that vector thrust, which is the only way I can think I can balance things. If somebody knows about another way, by the way, you cannot add wings, okay, I know that was easy, so you have this, but somebody can think about that, just let me know. But I think that is the only way, and for the movies also probably we can see that there are some thruster here and here, and we can balance that. So that will be the difficult part. So the easiest mechanism to control that maybe will be a on-off switch, but that is not no good here. That is for your air conditioner at home, that you on-off. Here we need something more active, okay? So basically I already have something working, but I have a control system in Python. I can link it with this software that I'm using, but that is future releases. So also we look at the Mach number. So here we have a free stream of 0.3, and see that in this case we haven't reached the critical Mach number, so everything is okay. We can see some separation here and here, but then we go critical free stream Mach number 0.6. We have our pressure distribution, okay, and we start to see here some low pressure. But when we look at Mach number here, we start to see that we have those critical regions. So namely here, we can cross-reference with pressure, and this is will start to create problems, and those non-linearities that we see computing the aerodynamic performance, you have it there. So I increase 0.75, where you're going to have shock wave here in many zones, so things will get really bad, and the performance will be, LD will be even worse, and who knows what other problems thermal heating for sure is going to cause some problems. Well, we know that is a crazy alloy that we have, the alloy that using there. And just to compare also all those results, those figures were 0 degrees here, just to show that 0 and 12 degrees, and just to show, to demonstrate how unrealistic. Already everything here is science fiction, unrealistic, but how unrealistic is here now. We don't see in the movie that it is in cruise condition at 12 degrees now with this incidence. So how unrealistic it gets when you increase that, and if you want to keep it low, to generate the necessary force at Mach 0.3 or 6 or whatever, okay? So we also have these results, okay, and here you have more separation, okay, comparing both cases, and that can cause some linear and non-linearities. So basically, to remember that all the data were put in here, okay? So feel free to join me in here and to help them to do some results, something more interested, because it's science fiction. It doesn't mean it's something that it cannot be shared with the communities for those doing science. So something I think can be published. Very interesting is the control system, okay? So that's what we want to control. And just to remind you that everything that we're doing here is exactly how you do the aerodynamic analysis of an airplane. But the airplane, you have the winds, okay? Here you have that, okay? So basically that's what we're doing. Okay, so I think that's all for this video, okay? Hopefully the next one is not going to take me that much time. Actually, I already have the results, so it's just creating the presentation, putting everything, and just getting also with my life and doing many stuff. So thank you for your attention. See you next time. Enjoy and have a nice weekend for those that knows that today is Friday. Okay, bye bye.